Good morning, everyone. Welcome to our NMIS Insights webinar this morning on machining innovation at NMIS. If you could just bear with us, please, for a few moments, just to allow people a chance to connect and join in. Thank you. Thanks very much for your patience, and I'll now hand you over to Crawford Cullen. Thank you. Enjoy today's webinar.
Thanks, Debbie. Good morning, everyone. Thanks for taking time out of your schedule to attend this NMIS Insights Online event, Machining Innovation at NMIS. My name is Crawford Cullen. I'm a Senior Manufacturing Engineer in the Machining and Additive team within NMIS and Technical Lead on Machining. If you just move on to the next slide, Karima, please. Just like to go over some housekeeping first. The webinar is being recorded and will be made available on the YouTube channel. Your microphones and webcams will be turned off during the session to avoid background noise. If you could type chat questions through the session via the chat tool, and we'll answer them at the end of the session. And use the hashtag NMIS Insights for any questions on Twitter. And if possible, could you take some time out of your day to complete the survey that we'll issue at the end of the webinar. So today's speakers, I've already introduced myself, Crawford Cullen. We then have Karima Hilton, a manufacturing engineer within the machining and AM team, followed by Conor McFadden, manufacturing engineer in the machining AM team as well. Then Peter Hammond, technical director at MSP, and then Stefan, an applications engineer at MSP. So the content today, I'll give a brief overview of NMIS and AFRC, and then the two NMIS employees will talk about the machining themes that are being currently developed at NMIS. Kima will talk about composite machining and machining 4.0, and Conor will talk about machining connectivity. Peter Hammond will then do an MSP introduction, and this chat will be about measure twice, cut once. And then Stefan will do a demonstration of MSP and the software available. This is software that's widely used at NMIS. So what is the National Manufacturing Institute Scotland? The National Manufacturing Institute is a group of industry-led manufacturing, research and development facilities where research, industry and the public sector work together to transform skills, productivity and innovation to attract investment and make Scotland a global leader. NMIS will increase productivity by reducing barriers to innovation, stimulate investment and increase manufacturing competitiveness, catalyse job creation and strengthen supply chain links, and inspire and attract talent and equip current and future workforces with the skills they and businesses need. And they'll work with manufacturing businesses of all sizes in multiple sectors, providing benefits across the whole of Scotland. So NMIS is operated by the University of Strathclyde, but supported by the Scottish Government, Scottish Enterprise, Highlands Islands Enterprise, Catapult UK, Skills Development Scotland, Renfrewshire Council and Scottish Funding Council. The NMIS Group, as you know, AFRC and LMC are already well-established centres. 2 seconds, sorry. The specialist technology centres are well established, but we're now waiting on the Manufacturing Skills Academy, Digital Factory and Collaboration Hub to physically open. Work has already begun and we're open for business. The Manufacturing Skills Academy already has continual professional development courses in place, and work has already been done by the Digital Factory by the AFRC's digital team. So in summary, the NMIS building has been approved and although not open, Work has definitely begun and support is available to you. So just before I introduce Karima, I'd like to touch on the purpose of this, which is the first machining webinar. The whole process of manufacturing a part is complicated and involves many processes. But before we even start that, we need to know, is the machine tool we have or the machine tools we have capable of manufacturing that part? And this is where MSP come into their own. Their software tells us if our machinery is capable of making the part, and if not, what needs to be done to rectify that machine tool so the part can be made. Then with a high value component such as a casting or a forging, maybe a lead time of 12, 14 months, MSP then tells us, can we make that part from that forging or that billet that is supplied? Once this has been done, MSP can then carry on and continue the part, continue to inspect the part. Does the part conform, or do we need to change or alter the program? So I felt that was a best place to start with a machining webinar. As I said, hopefully these will continue and we'll touch on other subjects that may be important to you in your process or in your manufacturing. With that, I'd like to pass you on to Karima Hilton. Thank you.
Thanks for that, Crawford. Okay, so I'm Karima Hilton. I'm a manufacturing engineer at the NMIS team. And I am leading the Machining 4.0 project. If you haven't heard of it, it's a European funded project and it's aimed to help SMEs around Northwest Europe. So we are aiming to transfer knowledge on innovative technologies to SMEs to make them more competitive with the rest of the world. The project itself consists of 10 partners, and these partners are located in Germany, Switzerland, France, Belgium, Netherlands, Ireland, and ourselves in Scotland. So we're covering quite a lot of the Northwest Europe region. The aim of this is really to really capture a lot of the small to medium-sized enterprises around these regions and try to make them more innovative. There are three main deliverables of this project. One of them is to create technology sheets. So these are one-pagers that we have on the Machining 4.0 website. There's a link following in the next couple of slides that you can go to. These technology sheets are coming from all 10 partners, and it tells you about different technologies that these partners are experts in. Please feel free to have a look at these sheets. There's lots on there, variety of from machining technologies to Industry 4.0 technologies, production tools. If you have any questions about these technology areas, it actually will tell you which partner has posted these sheets, and there will be contact details for you to get in touch with each partner, whoever you would like to. Also feel free to get in touch with myself, and I'll be happy to direct you to the right person. Another deliverable of the project is the voucher system. So we have 50 vouchers that we can basically help 50 SMEs around the Northwest region. The value of the voucher is 12,000 euros of our time. So it's basically passing on our expertise, allowing SMEs to use our equipment and our technology areas, really just to show the SMEs the technologies that are out there and to prove to them that they're actually worthwhile, but without them having to spend money on it at this stage, they can test it out. So to go about a voucher, I would say to get in touch with myself or any of the other partners, and we can discuss how we can go forward. And if we end up realizing that there's a means for the voucher, then please go onto the website and you can fill out a form. The main criteria are you have to be an SME within the Northwest region. It would be great if you're willing to share about the project that we will work on together. We could share it to other organizations and put it on the website. And the content of the voucher should be in the field of machining or Industry 4.0. So we do request that the organizations are machining SMEs. And the third deliverable of the project is application demonstrators. So all the partners have different demonstrator application areas. The AFRC ourselves, our demonstrator is on machining stresses. So this is an area that we've done a lot of research and development in the past few years at the AFRC NMIS team. We have different equipment. So we've got a DMU 125, which is where we are going to show off our demonstrator in this case. But in the team, we have a lot more other machines on site. We're proposing to use our tap test kit, use a smart fixture, use a sensory tool holder. And all these areas, we're hoping to extract data from these technologies and display them on a dashboard, which my colleague Connor will talk a bit more later on. And we will extract data from these technology areas and try to analyze it and help the machining SMEs to understand what's happening when they're cutting parts in the future. If you have any more questions about this, please ask at the end of the question and answer, because I'm more than happy to supply information. Another area of our application is composites machining. So we recently brought in a Breton Raptor. It's dedicated to machining lightweight parts. We've installed our MSP software on it, which Stefan and Peter are going to talk about further. This is allowing the machine tool to be able to locate datums on complex parts a lot easier than traditional methods. And this will help us to machine lightweight parts to the as close to drawing as possible. So the Breton Raptor is a 5-axis high-speed milling machine. So it's good for machining composites parts, but also aluminium parts as well. So now I'm going to pass you on to my colleague, Connor, who's going to talk more about connectivity and dashboards. Thank you.
Thanks, Karina. So I'm going to talk to you today a little bit about machine connectivity. Can you click onto the first slide? Thanks. So if you've heard about machine connectivity, you've probably heard of things like the industrial Internet of Things or big data or machine learning. Maybe you've even gotten to the point of some of the communication standards like OPC UA and UMATI and Modbus. But for those of us that aren't computing science engineers or don't have a computing science degree, what does this actually mean? It wouldn't really be fair to call these buzzwords because they do all mean something, although they can feel like that in some senses. So if you're starting to just get started with machine connectivity, it can all be really quite overwhelming. If you're looking for a complete smart factory setup, you do need to know what these things are. So I would recommend that you speak to our digital team who are doing some really good work in this area. But if you just want a bit more of a simple quick start overview, that's what I'm going to talk about now. So talking about if you're a smaller machine shop, how you would get started on machine data. So the first question you always have to ask when you're starting to collect information is, what are you actually trying to achieve with your information? So based on that, we've come up with the following quite simple use cases. The first one is productivity monitoring. So if you're a production manager and you want to understand what your OEE is on your machines. The second level is for an operator that maybe has to run several machines at once. You don't have time to stand by each individual machine while you're running the program. So you need a quick view of what's happening on each one that you can quickly check on. And the third one is from a maintenance point of view. Maybe your maintenance department is quite far away and you want to see what that error is before you walk up to the machine. So what data do we actually need to do this? So the first thing that we need is machine availability. That's just, is the machine on or off? The next one is the operation mode. So is it in automatic mode, MDI, edit mode? What can also be helpful is the alarms and errors. So that's where your maintenance department might be able to see that before they walk out to the machine, or you might just want to keep a record of that for your own information, because you might anecdotally know that a machine always has the same fault, but you don't keep a record of it. So that's helpful to know. And the final thing that can be helpful is just the current program if you want to see what's happening and correlate that back to a part number. So what does that view actually give us? If we have that information, we can get a quick view of what is happening on each of our machines on the shop floor. So now we know what we want. How do we actually get that, and how do we present it? So there's a couple of options when you're starting out. You can go the DIY route, and there are some benefits to the DIY route. And we've got open source software available, so there's no investment required up front. And if you do it yourself, you will learn how the systems work, and you will get a really good understanding of your systems and what is and isn't possible. And you can develop all that to your own specific needs. The difficulty you will have with that is the stuff that is open source is quite limited in terms of its capability and what machines you can connect to. You might have to develop a lot of that yourself. You will have to have some programming knowledge and network knowledge. So not to the full extent of being a computing science engineer, but you need to be able to work around the basics. And you might have some limited capability. So even if you can connect to your machine, you might not be able to do everything you need to with that. The other option is the commercial route. So there are several companies around who will be able to provide you with a commercial integrated package for connecting your machine tools. In fact, some of our members at the AFRC offer some of these packages, and they may be in chat, so you can possibly speak to some of them about their offerings. But you will get more comprehensive integration. They work with all sorts of different machine tools, so you'll actually be able to talk to your machine. They will have fully supported applications, so you don't have to go developing it yourself. And they have quite extensive features, so stuff you might not have even realized you wanted, they will offer to you as standard. The drawback that you need to watch out for with that is the setup and the subscription cost. And it's usually not as expensive as you might think, so it is always worth checking out, but there will be costs involved. You might have a proprietary communication standard and a proprietary database, which is fine if you scope out your software to make sure that it does everything that you need it to do. But just bear in mind that if you want to expand your system later on, you'll want to think about how accessible your data is. And the other potential drawback from that is the lead time if you need to get purchase orders through and arrange for time for people to come onto site, whereas with the DIY option, you can just start right away. So what did we actually do? So we decided to, we had a look around to see what standards were available and what we could do ourselves. We found MTConnect, which is quite a well-developed standard. It's royalty free, so you can do what you want with it. And they have a lot of resources on their own GitHub page where you can just download existing adapters and agents. I won't go into the detail of how it all works in detail, but we have 5 machines that we normally work with, and we wanted to see if we could get these connected. So the first machine that we have, the most simple one, was our twin turret lathe, which is a DMG Murray NMIS 2500. So it's got MTConnect built in. So all we had to do was point our system at that, and we were getting data straight out. That was nice and easy. We have 2 machines that have FANUC control. FANUC have the FOCAS protocol, which is built into the vast majority of FANUC machines. I haven't encountered a FANUC machine yet that doesn't have it. There is on the MTConnect GitHub an open source adapter for the FOCAS system. So we were able to compile that, point it at the machines, and get data out. The other 2 machines that we were hoping to connect, we had a bit more difficulty with. They use Siemens 840D controls. And if you have the OPC UA license, you will be able to get an MTConnect adapter for it, but we don't have that license. So unfortunately, we haven't been able to connect those machines. But from a quick trial point of view, we have, within the space of a few days, managed to get 3 of our machines on the system. So once that data is on the system, what do you do with it? And what you're seeing on the screen here is a dashboard it's an open source software from a company called Trackhand. All you have to do once you've got your data on the network is point it to the IP address of that agent, and you will get all of your data presented. And really, the data is available just by dialing into the IP address, so you can write your own applications. You can create an MQTT application using Node-RED and read information from it. You can do what you want. So this is really just a quick start to give you a flavor. And hopefully that's demystified a little bit around the questions that you might have on machine connectivity. If you have any more questions on it, please feel free to get in contact with us. And with that, I'm going to hand you over to Peter Hammond from MSP.
Good morning, everyone. Yep, my name is Pete Hammond from, I'm the Technical Director here at MSP. It's Stefan who's going to be doing most of the work here, and all I'm going to do is give you a little bit of an introduction. Anyone who's been doing any DIY will be more than aware of that sinking feeling when you try to place a part that you've made into it, whether it be a piece of coving, a tile, a kitchen unit, a bracket, and you've realized that it isn't going to fit. It's either the wrong way around, it's too long, it's too short, or if it's coving, it's almost certainly mirrored. It's horrible. And we all remember in our woodworking days, well, those of us of that age that did woodwork and metalwork, that our teachers used to yawp on about measure twice and cut once. Measure it and make sure everything's correct before you actually affect it. Strange thing is that we visit probably, I would say our applications engineers probably visit 1,000 spindles a year, at least, I would think. And it's amazing how these machine shops and many machine shops, they don't follow this principle. They don't find that the part is wrong until it hits the CMM at the end, and then try to work back to what's the problem. So what we've tried to do is try and work out where the measurement needs to be and what you need to do. And as Karima has explained, the MSP system is not throwing away what you've got. What it's doing is it's implementing measurements in the process to make what you've already got produce good parts. And that's really what we're about. Now, when it comes to the actual process itself, our understanding in this digital world is that the whole manufacturing process is designed away from the machine in the CAM package. And that's where the process is thought about. That's the, if you like, the simulation of what's really going to happen. And so we wanted to make sure that we incorporate the measurement inside the process, from the CAM package to the measurement of the machine to validate the machine to the in-process measurements. So what we're going to learn from Stefan, and I hope you find it as interesting as I do, is how we go about doing that. The only thing I would ask you is, if you do come along to my house, please don't mention the kitchen units. Stefan.
So I'm Stefan. I'm an applications engineer at MSP, and I've been doing that for about the last 6 years now. My role covers a wide range of areas, both on the customer-facing front and on our product development side. I'm often found supporting customers both in the part and the process development, as well as helping them understand their machine performance using the NC Checker benchmark. Alongside my customer support role, I spend a lot of time developing the on-machine side of NC Perfect Part on the macro development, and testing that both on simulators in the office and on live machines.
To get started, I'll begin by explaining how our Perfect Part solution fits into the machining process. Like Pete says, we help stop companies from machining parts incorrectly and incurring huge costs through scrap parts or rework. We review a customer's whole process and work with them to eliminate errors from each stage, from CAD design all the way to inspection at the end of the process. Throughout my time at MSP, I've worked closely with NMIS on a range of projects and have seen firsthand how our products have benefited them. Today we will show the full Perfect Part process. This begins in the CAD office with creating the part programs. We then move to the shop floor. First we need to make sure the machine is capable. We do this using NC Checker. This uses a completely independent calibration and verifies the machine is in good condition. Once we are confident the machine can produce the part, we then move on to the part setup. Using NC part locator alignments, the part setup process is hugely simplified, and the part alignment and condition of supply is verified before any machining takes place. After the part is machined, we then check the part before removing it from the fixture to ensure it is correct before it leaves the machine. Today, we're looking at a composite winglet, which commonly faces many of the problems that our products solve, and is a type of part that we're often involved with. It has all the usual challenges faced on a near-net part, including difficult to fixture due to springback when it's released from the mould, and deformation when cooling. Critical features are not in the correct place for machining. Minimal excess material leaves no room for error. And counterbores that are difficult to machine to the correct depth due to the previously mentioned deformation. Manual setup methods can't account for these issues, or are extremely time-consuming, and usually result in a failed final inspection, leading to large amounts of rework, concessions, or even scrap. And this is where NC Checker and NC Part Locator comes in. It can correct for these problems before a cutter ever gets loaded into the spindle. The process starts in the CAM office, where the probing programs are created. These are created offline in the same CAD-CAM system as the machining programs, and are delivered to the machine in exactly the same way as your machining programs. These are all created beforehand, so there's no CAD on the shop floor, and the program control is retained by engineering. In this case, we're using CATIA to create our probing programs. In conjunction with CATIA, we're using our NC Inspect plugin. This allows us to add in all required NC Part Locator functionality without resorting to custom user commands or PP words, a struggle I'm sure many of you are aware of. By using NC Inspect in conjunction with CATIA, we have the benefit of the toolpath generation that we're familiar with, and have full use of all NC Part Locator functionality and are not restricted by the post. All of the information required to generate a full NC Part Locator report is contained in the probing program itself, including all tolerances and any process control variables. The programs can be created in any CAD-CAM system of your choice as long as it supports the generation of probing programs. Depending on the part issues, a program can be quite simple or quite complex. Multiple alignments can be generated, and offsets for counterbores or tight tolerances can be probed. So once we've created the probing programs, we can look at what happens on the machine, starting with NC Checker. NC Checker assesses the performance of the machine tool to check it is capable of machining parts within tolerance. This is particularly important on 5-axis machines, where any machine errors, in particular in the rotary axes, will have a major impact on the machine's ability to machine the part within tolerance. To eliminate any sources of error in the probing results, this uses an independent probe calibration as part of the NC Checker process. This means that NC Checker results are not prone to any errors due to probe data faults that may result in invalid probing results. This calibration is used for both NC Checker and NC Part Locator, so we are certain the probing results are correct. The benchmark program is run on the machine. This is supplied as part of the delivery by MSP during the install. The benchmark consists of a series of checks that verify both the performance and repeatability of the probe, the reproducibility of the tool change, and the performance of the rotary axes. The rotary axes are assessed by measuring the sphere at multiple head orientations. Unlike other systems, NC Checker drives the machine exactly the same as in a machining program, for example using G43.4 or 5 or Triori. This means the checks correlate exactly to any errors you would see in a finished part. The results are displayed in the Perfect Part software, and the whole process is automated and can be run in about 25 minutes. The tests are designed to assess the machine kinematics over a full range of movement. The main test assesses the rotary axes on their own, as well as indicating where the machine is capable of producing parts within tolerance. The reports can be used to diagnose the type of error, and with a small amount of analysis can suggest parameter updates if these are applicable. Additional tests also assess the rotary axes over the full range of movement to give an image of the machine's capability over the full working envelope. After the programs are run, the benchmark is generated. The main benchmark report makes it easy for everyone to see the machine's capability at a glance by the colour of the wheel. This colour changes, going from green when within tolerance, changing to orange when starting to drift towards the upper tolerances, and finally red if the benchmark has failed. Each spoke on the wheel represents each test that has been run and whether the test was in or out of tolerance. If we look at this example, you can see we have a red benchmark. This indicates that one or more of the checks has failed. We can access each individual check directly from the benchmark. In this case, we can see that the machine has failed on the B-axis check and the combined B-axis and C-axis check. The C-axis check itself is extremely good at 10 microns. By reviewing the rotary axis checks, we were able to find the source of the error and correct the machine kinematics in the space of about an hour and a half. In this case, the error was down to an incorrect probe calibration when the machine was set up. Because we use a completely independent calibration for NC Checker, we found this error pretty easily. It's also possible to track these reports to monitor the performance of the machine over time. This makes it very easy to see if there's any change in performance and allows planning of preventative maintenance and other reactive maintenance with its associated machine downtime and loss of revenue that comes with this. Now we are confident our machine is capable of producing the part within tolerance, we can move on and look at the part setup itself. As mentioned before, a part like this will have some distortion, meaning complex fixtures and multiple options are normally required. NC Part Locator automates the setup process and has allowed us to simplify the fixture and allow access to all features in a single op. Here we've used a simulated vac fixture and we've simply placed the part on the fixture, set the datum by eye to within about a millimetre or two. NC Part Locator will easily correct for setup errors in the millimetre range, and if programmed correctly, can even correct for larger errors than that. The programs we created previously are run on the machine. Because all the process control and process tolerances have been defined in the program, the operators simply have to run the program the same as in any other machining. NC Part Locator automatically detects the type of process being run. The part is probed and the data is transferred to the Perfect Part software. Once the probing is complete, the software produces a series of reports, which we'll go through now. The initial report displays the measured data in its unaligned state. Whiskers on the model indicate the magnitude and direction of any deviation from nominal. This shows that if the part were machined with no alignment applied, the finished part would be incorrect. Proceeding on from the measured results, NC Part Locator calculates the best fit alignment. This is a full 6-axis alignment. We can align and unalign the views to see the translation that will be applied. Obviously this is exaggerated to make it clearer. We can also see the calculated XYZ shifts and the ABC rotations in the table. The final report shows predicted results using the measured data but with the alignment applied. This report is using the measured data, so as well as showing the predicted alignment results, it also is a good condition of supply check, and any out-of-spec parts can be rejected before machining. Not only is NC Part Locator helping you make a good part, it's also stopping you make a bad one. Proceeding on from the aligned report, the alignment data is transferred to the control, ready for use in subsequent machining or for other probing operations. Once the initial alignment has been generated, there are a range of subsequent NC part locator processes we can use. Because probing a free-form part will inevitably contain some cosine errors, and an iterative alignment can be run to further refine the alignment. For parts where local features are critical, we can also create multiple alignments that are only applicable to that feature, for example an access panel in a wing skin, or a PCD in a forging. We'll usually run a pre-machining check after an alignment has been generated, and before we do any machining, to verify that the alignment is valid. This normally includes the points used for the alignment, but again, additional points can be added to create more complete condition of supply check. Should this process fail due to points or features being out of tolerance, it will stop the program and prevent it carrying on. With multiple customers who've removed this after a number of parts, as they're 100% confident the alignment is correct and the time can be saved. The pre-machining process can also be used to perform in-process inspection and to allow cut, measure, cut type of operations. On composite parts, there's often a requirement for countersinks to a specified depth. Due to the nature of composite parts, maintaining the correct depth for every countersink can pose a lot of challenges. The hole offset process probes the part before the holes have been drilled and records the deviation from nominal. When the probing is complete, NC Part Locator generates a report showing these deviations. Tolerances can be used here to apply process control and make sure there's sufficient material. Once the probing is completed, the offsets are stored on the PC. These will then be recalled during the countersinking operation later in the process and apply a length correction to the tool, ensuring a perfect countersink every time. Once all the required alignments and offsets have been generated, we can machine the part. Because all the data is stored in the Perfect Part software, it can be recalled at the required point in the machining process. All probing can be completed before the machining. This means there's no risk of swath affecting the measurements. The part is then machined using the alignment. This is applied using a coordinate system translation and rotation that is applied via a subprogram call in the machining tapes. This is applied in all machining ops, from roughing through to finishing and drilling. During the countersinking operations, the offsets that we probed previously are recalled and activated before the countersink is cut. These are used on top of any alignments. After the part has been machined, a post-machining verification can be run to verify the part has been machined correctly. This probes the part using the alignment before removing it from the fixture, and lets us verify the machine fixtures are all correct. By probing the part on the machine, we verify the machining was correct before it was released from the fixture, and any springback from stress relief during machining has caused the part to deform any more. It's also very useful finding sources of error in any parts when errors are found in final inspection. By probing the part while it's still on the machine, we can also find problems immediately and not a couple of days later when the part's inspected at CMM. And many more parts may have been run by this time, potentially scrapping a number of parts and costing thousands. Some of our customers have hugely reduced or even completely eliminated the requirement for CMM checks by using NC Part Locator in their process. Our Perfect Part software stores all reports both from NC Checker and NC Part Locator in the archive. This maintains full traceability throughout the process. We can search and view all of the reports via the archive viewer, and the reports can be exported for sharing with other parties. And so we've come to the end of the machining process using our Perfect Part solution. We've seen how the programs are created offline using the same CAM system as the machining programs. After this, we've made sure our machine is capable of producing the parts within tolerance, and if required, have been able to use the NC Checker benchmark report to improve the machine performance. We've then probed the part and generated an alignment or multiple alignments and hole offsets. The alignments and hole offsets have been used in machining programs to machine the part with any setup errors and thickness errors on the counterbores removed. Finally, we've verified the machined features on the machine. And that's all there is to it. By removing and checking for error at these stages, you can have full confidence in your machining process is extremely precise and will be producing good parts. Like I said at the start of the demo, these products have helped NMIS to monitor the machine performance over time and understand how the machines are changing. It has also given them the ability to reduce setup time and use simplified fixturing to hold complex parts. We can also carry out in-process measurements of test cuts.
So I hope this has been interesting for everyone. We've looked at a solution for a typical composite part here and seen how some of the NC Perfect part processes are used and applied to dealing with issues. While we've shown a composite part here, the same principles can be applied to any other type of part really, in particular near neck parts such as castings or forgings, and this is where we've helped a lot of our customers, including hot forged, cold forged, castings, additive parts, additive in particular. So thank you for listening. I'm going to hand you back to Crawford to field any questions that anyone may have sent in.
Thank you, Stefan. I'd just like to carry on from what Stefan's saying. MSP are tier 2 members of NMIS and maybe arguably one of our most active members. This software is run on all machine tools within NMIS, and it's essential in collaborating what we've been doing on distortion with the FEA guys. What we'd like to see is the technology is in NMIS. If anyone feels the need to come in and maybe have a demonstration, that's something we can set up for you. You can come in and see the technology running on machines. We can run a demonstrator for you, either on one of the large machine tools, the Breton, which is a 5-axis gantry that Karima showed, that's I think 4 meters by 2 meters by 1.5, or down to NHSC die making 5-axis that we use. This technology, I believe we might be the first, Peter could back this up, but we have an LMD, an additive and subtractive hybrid machine, and MSP are also installing that, working along to put that on this machine, which is going to be essential for the work we're doing in additive remanufacturing or feature adding to parts. So as I said, if anyone has an interest, please drop us a line and come along and we can give you a demonstration. I mean, maybe get the guys from MSP to support that as well, or we can show you. I don't believe we've had nothing on the Q&A. Karima's answered VG about the access to the slides for the technology, and a couple of comments from GOM and Sandvik, also members at NMIS. As I said, we have a variety of members in the machine and additive team. We're very active with our members, and we encourage people to come along and work with us and them. With plenty of support available. Sorry, something's just come up. So Stefan's, I've got one here from John. It's a nice presentation. There is no mention of temperature, its measurement and inclusion for effect. The larger the machine, the bigger the problem. Do you take temperature into account?
I'll answer that if you like, Crawford. Yeah, thank you for that, John. It's actually quite a big thing, temperature and the effect. So on some of the systems we have, I know the Breton has this capability. They do have the ability to apply thermal compensation. However, what we found is that the biggest cause of thermal issues is having manual steps where the machine is turned off there's manual interventions whilst the part is checked before the machine is turned back on again. And what that means is the actual thermal gradient of the machine moves as well as the environment. So by doing in-process probing, which is fully automated, you can't eliminate it, but first of all, what you can do is you can reduce the effect on the actual machining part itself. But there's also another element, and that is that we want to see what effect it has. So you saw in the video that we were measuring a sphere, and there is a standard test. It's applied on coordinate measuring machines, but you can apply it equally using NC Checker, and that is called a drift test, whereby you're monitoring the temperature and measuring that sphere, and then you might do a warm-up cycle, and at regular intervals you repeat the measurement of the sphere. And what you see is the effect of the warm-up cycle, if you like, or the environment on the movement of that sphere. And so although what we don't do is we don't compensate for it. Our role is to measure something so that we can inform people of what the conditions are. So if we look at a drift test, we can say a machine will vary by X microns over this thermal gradient. So we don't apply the correction, we just inform of what the state is, which actually feeds back into Connor and is, machine interface. I hope that answers your question.
Yeah, just I would go on the back of that, Peter, and say as well that we would be looking to develop closed door processes where using MSP and the CAM package, when the part starts, the machine won't be opened again. So eliminating operator interaction, opening doors, things like that. So part will be checked, probed, datum set, and ran and inspected in the machine without any interaction. What we've done with the Breton, the large scale machine, is we've built an enclosure around it, so we have a temperature controlled environment that machine sits in at 21 degrees, and hopefully that eliminates some of that as well. Mm-hmm. Hope that answers your question, John.
Yeah, I should also add, you just reminded me that we have a number of Breton machines that we're using. One of them is in Australia, and it's not in a thermal environment, thermally controlled environment. It is in a workshop, but that machine shop does vary over time. So what they've done, we have a test called a machine position validation, whereby inside the large envelope, and it's a 5-meter machine, I think, they have a series of spheres located. And when we benchmarked the machine, we measured those spheres and we set those position as a reference. And then throughout our intermediate benchmark, what we're doing is we're seeing if those spheres have apparently moved whilst recording the temperature. So we can actually see over time that as the environment changes, what the actual effect has within the volume of the machine. So as I say, we measure the thing as opposed to applying it.
So John's asking, is it quicker with a laser tracker?
Well, the actual process that we use they are complementary, John. What you would do is you would use your probing to show that there is something not quite right, at which point you could put the tracker on to try and identify the cause. The reason we're saying that is that our probing uses the same kinematics and algorithms as the cutting. So our measurement is determining what the end piece part would be. If you have an independent measuring device like a laser tracker, you've then got to somehow correlate that back to what the tooltip of the machine would do. So if, for example, there was an orthogonality problem on the machine, the laser tracker is a much better solution because it's going to define it. But what we'll decide that that is the problem that you're trying to identify. So the two are complementary. We use Checker to validate that the machine is the same today as it was yesterday. And if it is different, then we can point at where the possibility of the problem lies. And then it may be that a ball bar, a tracker, kinematic correction software, or an actual mechanical refit is necessary, or backlash. So these are all things. We just identify them. We don't try to solve the entire lot of problems.
Just to add to what Pete's saying there, because NC Checker is run by the operators, it can be included in the schedule for the production. So say a lot of our customers will run it at the start of a high value part to make sure the machine can actually do it, and that'll take them the sort of the machine position validation check that Pete mentioned. That itself takes 5 minutes to run. So if you can spend the 5 minutes to run it, if it's all good, then you know you're good to produce your part. Otherwise, you know that you can then get the laser tracker in, which is obviously going to take a little bit longer. So it's a quick check, so you know your machine's capable.
Thanks, Stefan. Yes, it's part of our technicians' monthly checks that they run on the machines. Definitely weekly and monthly checks, and MSP will be run every month to see if there are any errors. I think there's no more questions coming in by the looks of it. At this point, I'd just like to say thank you to the presenters, Karima, Connor, Peter and Stefan. Thank you very much. Very informative. It's not in dispute. I think this software is tremendous, and it's imperative that NMIS use this and continue to develop the partnership we've got with MSP. Thank you all very much. I'd just like to hand over to Debbie now. Thank you.
Thanks, Crawford. Yeah, and just once again, thanks very much to Peter and Stefan from MSP and for the NMIS machining team for taking part in today's webinar. Thanks to everyone again for joining. Our next NMIS Insights is next week. It's on the 2nd of December, and it's on the subject of sheet metal forming simulation. You can find details on our website at nmis.scot. I'm just going to bring the webinar to a close now. Thanks once again for joining us.